Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video discusses the differences between expected and observed frequencies and how to obtain them. Let's get started. So, from what we saw in the previous mini lecture, obviously we need to identify first the observed frequencies and the expected frequencies. We're going to actually need those to calculate our test statistic. Now, again, I want to emphasize that you're going to be using StatCrunch for a lot of this, but it's helpful to know what the computer software is doing for you in the background. So how would we do this using the old school method? That's what we're going to go through here right now. So we find the expected frequency with one of two approaches. We're actually going to assume that all the expected frequencies are equal, in which case we just take the total sample size and divide it by the number of categories, because if all the frequencies are equal, then they're equally distributed amongst the different categories of our data. If the frequencies are not equal, then we just calculate, based on the probability for each individual category. Let's consider an example. So we've got a single die, we roll it 45 times, and this is the results that we get. So we've got 13 times we rolled a 1, 6 times we rolled a 2, 12 times we rolled a 3, so on and so forth. The probability that we would expect to get from a fair die would be that any of the 6 outcomes on the die are going to be equally likely. You get a 1 out of 6 chance of rolling each number. So then that means all we do is just take our observed frequency, okay, and that's going to be, so for the first outcome, it's going to be the 1 there, or actually, back it up. If all of you are equal, then we just take the total number and divide it by the number of categories. So we've got 45 rolls, 6 categories, so therefore 45 divided by 6 is 7.5. And so each of our expected frequencies is 7.5. Because we're assuming it's a fair die. But wait a minute, not all outcomes are always going to be that way. They're not always going to be equally likely. So let's revise our example with the dice roll. Suppose now we have one die, we roll it 45 times, but now it's not a fair die. So now we've got a different probability of rolling a 1 than we do any of the other numbers on the other sides of the die. Now how do we calculate the expected frequency? Here you're going to take the probability for each column and multiply it by its respective observed frequency. So we've got 45 rolls of the die, but now we're going to get our expected frequency from n times p. So this means each outcome has a different expected value. So for the first outcome, where we're rolling a 1, we're going to take that total number of rolls, 45, and multiply it by the probability of rolling a 1. That gives us 22.5. So we would expect the frequency count there to be 22.5. For all the other numbers that are not 1, we're going to have, notice we have the same probability. So we're just going to do the same calculation for each of those. 45 times that probability gives us 4.5. And so that's going to be the expected frequency for the remaining categories. Now, theory doesn't always mirror practice. So the sample frequencies that we observe could be quite different from those we expect from our theoretical prediction, as we just saw in the previous example. This difference begs an important question. How much of a difference does it take to be statistically significant? Okay. So how large does that difference need to be in order to be statistically significant? We answer that question with our test statistic, which we learned previously is the sum of the the square of the differences of our observed and expected frequencies divided by the expected frequency. So here's our chi-square distribution. Remember, we got a right-tailed test with goodness of fit. So we've got the right tail there colored in as our region of rejection. If the values for O and E are close together, the difference between them is going to be small. And when you square a small number, you get an even smaller number, typically, especially if the number is less than 1. So that means that chi-squared is going to end up being small, because you're taking a lot of small numbers and adding them together. So chi-squared is going to be small, and it's going to be outside the region of rejection, outside that critical region. Because we're outside the region of rejection, we fail to reject our null hypothesis. That means the null hypothesis could be true. Remember, if we're rejecting it, that means we know it's false. If we fail to reject it, well, it might be false, but it might also be true. So we have to conclude the sample data could have the claimed distribution, because that's what the null hypothesis says, that the distributions match up. Alternatively, if we're inside that region of rejection, we get that because the differences between O and E are not, they're not small, because O and E are not close together. So the differences are going to be large. And that, you take a large number and you square it, you get an even larger number, and that's going to make chi-square really large. So that's going to put you there in that right tail of the distribution where you've got your region of rejection. Of course, when you're inside that critical region or region of rejection, you're going to reject the null hypothesis. When you reject the null hypothesis, which says that the two distributions match up, you're going to conclude that they don't match up. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.